Picture this. You have like a brilliant idea for a new software project.
Oh, yeah. The caffeine is flowing.
Right. You're energized, caffeine in hand, you're ready to build. But before you write a single logical function, the modern development chore list begins.
It's exhausting.
It really is. You need version control. So, you initialize a Git repository. You need to document your architecture. So you go set up a wiki over on GitHub or maybe spin up a Confluence space.
And then the project management overhead kicks in. You need a way to track issues.
Oh, exactly.
Right, so you find yourself configuring Jira workflows or like GitHub issues. And if you want to map out the system visually, you're suddenly authenticating into draw.io or Lucidchart.
Yeah, and if you plan to discuss any design decisions with anyone else, you're probably starting a Discord server or a Slack workspace.
Before you've written any code.
Exactly. It is an overwhelming amount of friction just to get to the starting line. We have completely normalized this massive distributed tech stack for even the smallest, most experimental projects.
We really have. I mean, you are managing half a dozen accounts, API tokens, integrations, all before you even compile a simple hello world.
Okay, let's unpack this, because setting up a standard project today is a lot like buying an empty plot of land.
That's a good way to look at it.
Right. Sure, you own the land, but you have to go source every individual brick, every copper pipe, every window pane from a dozen different vendors just to build a basic shelter.
It's just a constant context switch.
Yeah. So the mission of this deep dive is to explore a radical alternative. It's a philosophy that directly challenges that fragmented approach.
We are looking at Fossil DVCS today.
Yes, Fossil.
It's a distributed version control system that acts more like getting the keys to a fully furnished off-grid house.
Where the pantry is already stocked.
Exactly. The generator is humming, everything is there. We're going to examine how an entire project's life cycle, from the raw source code to the educational curriculum, the bug tracker, and even the chat server, can be completely contained within a single 25-megabyte file.
Which just sounds impossible, right? So to really understand how this works in practice, we are exploring a specific case study from our sources. It's an embedded software project called FURS.
Spelled F-U-R-S.
Right, which stands for Fourth Upload Replacement System. Let's talk about what FURS actually does, because it sets the stage perfectly for why a tool like Fossil is so necessary here.
Sure. So FURS is a specialized tool built for STM32 microcontrollers.
And these are tiny chips, right?
Tiny. Storage space is an absolute premium on these things. Usually, when you are programming these microcontrollers, the chip has to store all these massive human-readable string names.
Like the CMSIS register names.
Exactly. The CMSIS register names. It stores them in its onboard flash memory just to map them to physical hardware addresses at runtime.
Which takes up a ton of space.
A huge amount. Each character in a string like a GPIOA_base takes up precious bytes. And the lookup tables to resolve them, they consume even more.
So how does FURS fix that?
Well, the FURS project solves this by shifting that entire resolution process to the host computer.
Oh, wow.
Yeah, so by the time the code actually reaches the tiny microcontroller, it has already been stripped down to raw, direct hexadecimal memory addresses.
That's brilliant.
It is. That single architectural shift frees up about 45% of the chip's flash memory.
45%. That is massive.
It's a game changer for embedded systems.
But building a system that complex requires intense focus. And, as a solo developer, you are constantly battling that context switching we talked about.
Right, the fragmented plot of land.
Exactly. You are leaving your code editor, opening a browser, logging into an issue tracker, writing a ticket, jumping over to another web app to check a diagram.
And then trying to get back into your terminal.
Right. Every time you cross those application boundaries, it shatters your focus.
And that is the fundamental architectural difference between standard Git and Fossil. We all know Git. It is the absolute industry default.
Yeah, everyone uses Git.
But underneath, Git is essentially tracking a directed acyclic graph of file tree snapshots.
Right.
It knows what your files look like at a specific point in time, and it ends there.
That's its only job.
Exactly. Fossil, on the other hand, doesn't just track files. Beneath the hood, a Fossil repository is actually a complete SQLite relational database.
Wait. I have to play the skeptic here for a second.
Go for it.
Putting your entire project, like the code, the tickets, the wiki, everything, into a single SQLite database file. Isn't that a massive single point of failure?
A lot of people think that at first.
Because if that one database file corrupts, my whole project vanishes. Doesn't that violate the core Unix philosophy of do one thing and do it well?
Oh, it absolutely violates the Unix philosophy.
Really?
Yeah, Fossil is notoriously anti-Unix by design. But regarding the single point of failure, we have to look at what SQLite actually is.
Okay.
It was created by D. Richard Hipp, and fun fact, he also created Fossil specifically to manage SQLite's development.
Oh, I didn't know that.
Yeah. And SQLite is arguably the most tested, widely deployed, ACID-compliant database engine in the world.
It's everywhere, right?
Literally everywhere. It powers the internal storage of every smartphone, every web browser, most smart cars on the planet. It doesn't randomly corrupt.
Okay, that's reassuring.
When you download the Fossil binary, you are downloading a tool built by database obsessives. You run one command in your terminal, just type Fossil way, and it instantly spawns a complete web server on your local machine.
Usually on port 8099, right?
Exactly. No Docker containers, no complex DevOps pipelines, no cloud dependencies whatsoever.
So you are telling me that a solo developer with like zero DevOps background gets a full stack project management environment running locally in seconds.
In seconds. And that self-contained environment completely changes how a developer handles documentation.
How so?
Well, when your wiki is literally querying the same database as your source code, documentation stops being an afterthought. It becomes a first-class citizen of the codebase.
Oh, and the FURS project illustrates this beautifully.
It really does.
They have a built-in wiki with over 110 pages.
Which is huge for a solo project.
Right. And we are not talking about flimsy markdown redemes sitting neglected in some docs folder. These are deeply detailed engineering documents.
Yeah. The sources mentioned that thermometer page.
Yes, the thermometer page. It functions as a complete technical article on a digital temperature sensor demo, specifically for an LMT01 sensor.
And it doesn't just display code snippets?
No, it breaks down the physical hardware routing. It explains exactly why pin PA6 has to be externally jumpered to pin PA5.
Which is such a specific hardware quirk.
It is. It details how the comparator output simply cannot be routed internally on that specific silicon.
Right.
It is written for a human being trying to understand the physical circuit. And the craziest part, it lives in the exact same database as the firmware controlling it.
That is the beauty of it. And, visualizing those hardware constraints brings up another notorious pain point in software engineering.
Let me guess. Architecture diagrams.
You got it.
Oh, this might be my favorite technical discovery in the entire source material. We have all felt the pain of architecture flowcharts drifting out of sync with the actual code base.
It happens every time.
Every single time. Usually you build a beautiful diagram in some web tool, export it as a PNG image, and drop it into your repository.
Right.
But that PNG is a binary blob. You can't search its contents. You can't see what specifically changed from yesterday's version.
It's just a flat image.
Yeah. And 6 months later, when the architecture inevitably changes, nobody remembers where the original editable source file is hosted, or, who even has the password to the account.
And so the diagram becomes a dead artifact. It's actively misleading anyone who looks at it.
Exactly.
We do have tools like Mermaid or PlantUML to try and solve this with code-based rendering.
Sure.
But they often require external plugins or complex markdown processors to render properly in a browser. It's still friction.
But Fossil solves this natively, right, with its own built-in diagramming language.
Yes. It's called PICCHR, spelled P-I-K-C-H-R.
The FURS project relies heavily on this.
They do. They have a wiki page called Using FURS Flowchart that maps out the entire development lifecycle.
And the developer didn't draw boxes with a mouse. They wrote text-based picture markup.
Right. Instructions like draw a circle here, draw an arrow to a box there.
It's just text.
Exactly. And because the Fossil binary has the picture compiler built directly into it, it parses that text and generates a lightweight SVG graphic inline.
Right there in the local web interface.
Yes, the browser doesn't have to fetch any external libraries at all.
And the practical advantage of that is just huge. Because the diagram is just text, it is greppable.
Oh, that's a great point.
Yeah, you can run a search across your entire project for the word database, and it will actually find the specific box in your diagram.
And it's stealable.
Yes.
Yeah.
Meaning when you look at your commit history, you see the exact line of text where an arrow was redirected.
So the architecture diagram is perfectly versioned in the exact same commit as the source code that changed the architecture.
They evolve together. They can never drift out of sync.
It's so elegant. And once you have a system that tightly couples the code and the visual architecture like that, the next logical challenge is knowledge transfer.
Right.
You've built this complex STM32 memory resolution tool. How do you teach it to a newcomer? Or, perhaps more commonly for solo developers, how do you remind yourself how your own architecture works when you revisit the project 6 months from now?
Here's where it gets really interesting.
I love this part.
The FURS project doesn't just provide like a quick start guide. The developer integrated a literal curriculum into the repository.
Inside the repo.
Inside it, there is a wiki page explicitly titled Study Guide.
Though calling it a guide almost undersells it.
It really does.
The source material outlines a comprehensive academic module living inside the version control system.
Right.
It includes a 10-question short-answer quiz testing the user on core concepts, like the nuances of the 4-stage transformation pipeline.
And it provides a full answer key.
Yes, and a complete glossary that strictly defines specialized technical terminology. Words like bitfield, CMSIS, and REPL.
It even pushes beyond rote memorization by including essay questions.
Essay questions in a code repository.
I know, it's wild. It prompts the reader to think critically about the underlying philosophy of the software. It asks them to defend trade-offs.
Like weighing the benefits of runtime efficiency against code readability.
Or the costs of build time resolution.
Right. Now, consider the alternative for a moment. If you build an open source project today and want to offer that level of educational depth, where does that curriculum go?
It usually gets published on a third-party educational platform.
Exactly. Maybe a Notion workspace or a series of Medium articles.
But what happens if those platforms shut down?
Or what if they pivot to an enterprise-only pricing model and lock your educational materials behind a paywall?
You lose the ability to teach your own users. But by integrating the quizzes, the glossary, and the study guide directly into the FOSS database, you guarantee that the knowledge transfer mechanism is never separated from the tool itself.
As long as a user can clone the code, they automatically clone the teacher.
That is such a powerful concept for beginners. You don't have to go hunting for tutorials. It's all right there.
It is. And that seamless integration of context is vital as a project moves from its initial setup and onboarding phases into the messy reality of long-term maintenance.
Because software inevitably breaks.
Oh, bugs happen. Iterations are required. The way we record that history drastically changes how we understand a code base years later.
Yeah, think of standard Git, like a highly accurate security camera. You type git log and you get this sterile mechanical list of disconnected events.
Fix makefile typo.
Update dependencies.
Resolve merge conflicts.
Exactly. It records precisely what happened and when it happened, but it offers zero insight into the developer's mindset. Fossil's timeline, by contrast, is like having the director's commentary track playing over that security footage.
I like that analogy.
You get the mechanical action plus the emotion, the frustration, and the logic all in one place.
And the FURS timeline provides a perfect example of this narrative value.
Oh, Terry Porter's logs.
Yes, the primary developer, Terry Porter. He practically uses the Fossil timeline as an ongoing engineering diary.
You can trace a genuine emotional arc through the project's history, like the logs start way back in 2015.
And they are heavily colored by the sheer frustration of a developer forced to type out 4,000 obscure register names by hand.
Reading them line by line from a massive, dense technical manual.
You can feel the burnout.
You really can. And then you follow that thread all the way to 2023, capturing the exact eureka moment when he cracks the architecture for host-side resolution.
The check-ins are remarkably human.
There's a specific entry where he just drops all formalities and writes, let me quote this, "Bug J, I forgot to include registers.pat in the makefile. Do it now."
I love that. That shift from a sterile changelog to a contextual diary is profound. It captures the panic of a broken build, the sudden realization of a missing file, and the immediate action taken to fix it.
And when it comes to tracking larger issues, Fossil's approach to bug management is fundamentally different from the industry standard.
It is. Normally, your code base lives in your terminal, and your bugs live in a totally separate database owned by Atlassian or Microsoft.
Right. But in Fossil, the bugs are versioned artifacts within your own SQLite database.
Exactly.
The sources detail the second most recent check-in on the FURS timeline. It isn't just a quick note. It is a massive 15-item bug report.
And the report spans multiple severity levels, from critical system failures down to low-priority tweaks.
And because Fossil treats tickets as native artifacts, this nearly 500-word report is embedded with inline SQL snippets.
Demonstrating correct join orders for the database queries.
Yes. But most importantly, it is assigned its own cryptographic hash.
That cryptographic hash is a crucial detail.
Why is that so important?
Well, in a standard web-based issue tracker, Someone can quietly go in and edit a JIRA ticket 3 weeks later to cover their tracks.
Oh, like changing the original requirements so it looks like they didn't make a mistake?
Exactly. But in Fossil, because that bug report is hashed and permanently etched into the immutable timeline, the history is cryptographically sound.
So you can't fake it.
You can't. You can check out the repository and see the exact state of the entire code base, the precise second that specific ticket was filed.
Wow.
There is no synchronizing of webhooks, no API rate limits. It just lives locally.
Which naturally leads to the question of scale, right?
Sure.
An embedded project like FURS might be managed by a solo developer, but what happens when a project gains traction?
When you start getting collaborators.
Right. If you have this beautifully self-contained, off-grid house, how do you handle inviting a team of collaborators inside without rebuilding your entire infrastructure?
Fossil anticipates that moment entirely.
Right.
Built directly into that same 25-megabyte binary are threaded forums and a real-time chat server.
Built in.
Built in. They sit dormant while you work alone.
Okay.
But the moment collaborators join the project, you don't need to provision a new Slack workspace.
You don't have to evaluate Discord moderation bots.
You simply toggle a setting in your local web UI, and your team can start debating pull requests and architecture decisions in threaded forums right alongside the code they're discussing.
I know what you might be thinking, though.
What's that?
If everything, like the chat logs, the wiki, the code, the bug, hashes, is stuffed into one database file, won't it eventually hit a scaling wall?
That's a common concern.
Doesn't a single database struggle with massive gigabytes of data compared to something like Git large file storage?
That's a very fair technical challenge. Fossil isn't designed to manage a 300-gigabyte repository of uncompressed 4K video game textures.
Right, you wouldn't use it for that.
No. It is explicitly optimized for source code, text-based diagrams, and engineering documentation.
So for the vast majority of software development, the database remains incredibly lightweight and performant.
Exactly. And if we connect this to the bigger picture, optimizing for self-containment exposes a massive vulnerability in how the modern tech industry operates.
How so?
Well, we have built our workflows on a highly fragile web of third-party cloud services.
Oh, yeah.
When GitHub experiences a regional outage, development teams worldwide literally cannot work.
It's true. They lose access to their pull requests, their CI/CD pipelines, their issue discussions. Everything stops.
And if your external documentation host changes its markdown parsing engine, your complex architecture tables suddenly render as broken text.
Standard projects lose their context instantly because the context never actually lived with the code.
Exactly. The resiliency of offline self-hosting is staggering.
Because Fossil is a self-contained STIP-Lite database, you can run your entire project completely disconnected from the internet.
Anywhere.
Imagine you on a long-haul flight with no Wi-Fi or working from a remote cabin.
Off the grid.
Literally off the grid. You fire up your laptop, type Fossil-E, and you have full, unrestricted access to your wiki, your historical bug tickets, your rendered picker flowcharts, and your past forum debates.
You are never locked out of your own intellectual property.
Exactly how resilient is it, though?
Well, your entire project's lifecycle is completely backed up the moment you drag and drop that single database file onto a USB flash drive.
Just copy-paste the file.
That's it. You could hand that physical USB stick to another developer, and you aren't just giving them a folder of text files, you are handing them the entire functioning universe of the project.
It redefines our fundamental understanding of what a repository is meant to be.
It really does. It is no longer just a digital filing cabinet for text documents. It is a living, operational workspace.
So what does this all mean? When you synthesize the self-contained wiki, the text-based diagrams, the integrated curriculum, and the narrative bug tracker,
It all comes together.
the name of the tool itself becomes incredibly poetic. Yeah. A fossil in the natural world isn't just a dead bone. It is a heavily compressed artifact that contains the complete evolutionary history, the literal DNA of a complex creature.
I love that.
With Fossil DVCS, you dig up this one, single file, and you have everything you need to reconstruct the entire software project exactly as it lived, breathed, and evolved.
It's beautiful. And it leaves us with a provocative final thought to ponder.
What's that?
For decades, the software industry has viewed version control merely as an auditor. Cold mechanical tool designed strictly to track what code changed.
Right, the security camera.
Exactly. But if our daily tools naturally captured why it changed,
Oh, wow.
if they inherently preserved our developer moods, our failed architectural experiments, our chaotic forum debates, and our midnight eureka moments right alongside the source code.
How would that reshape the culture of software engineering for future generations?
Exactly.
It would mean we finally stop leaving empty, undocumented plots of land for the next generation of developers.
And start handing them the keys to a fully furnished house.
History and all.